Welcome to this lecture on probability, mass, and density. Today, we are going to explore how we measure and distribute certainty when dealing with multiple random variables at the same time. Whether you are predicting the weather, analyzing financial markets, or studying biological traits, understanding how different variables interact is absolutely essential. Let us dive in and build our intuition from the ground up. To begin our journey, imagine you have exactly 1 kilogram of sand and you need to distribute it. In statistics, this sand represents our total certainty, which is exactly 100% or the number 1. When we study multiple variables together, like a person's height and weight, we group them into what is called a random vector. A random vector is simply a list of variables that have random outcomes, written together as a single mathematical object. Our goal is to understand exactly how our 1 kilogram of certainty is distributed across all the different possible outcomes of these variables. Now that we understand the idea of distributing certainty, let us look at the first way this can happen: discrete variables. If the variables can only take specific separate values, like the number of cars in a parking lot or the number of heads in coin flips, we are dealing with a discrete situation. Think of this as placing our sand into several distinct buckets. If you want to know how much sand is in a specific bucket, you just weigh it. Mathematically, we use a probability mass function, or PMF. The joint PMF tells us the exact probability that these variables will take a specific set of values all at once. Building on the concept of the probability mass function, we must establish a fundamental rule called normalization. Because we are absolutely certain that some outcome will happen, the total probability must always add up to exactly 1. In this formula, the sigma symbols mean to sum or add up. The variables x1 through xp represent all the different random variables we are studying. The function p is the joint probability mass function. By placing the sum symbols in front, we are mathematically stating that if you add up the probabilities for every single possible combination of these variables, the grand total must equal exactly 1. If it equals anything else, the function is simply not valid. Having covered discrete variables, let us shift our focus to continuous variables. If the variables can take any value within a range, like exact temperature or time, we use a probability density function, or PDF. Imagine taking that same kilogram of sand and spreading it smoothly over a large table. You cannot ask how much sand is at one exact microscopic point, because a single infinitely precise point holds 0 sand. Instead, the PDF gives the density or thickness of probability at that spot. To find the actual probability of falling within a certain range, we must calculate the area or volume under this continuous curve. Just as we normalize the discrete mass function, we must also normalize the continuous density function. However, for continuous variables, we cannot simply add up individual points because there are infinitely many of them. Instead of a regular sum, we use an integral, represented by the elongated S symbol, which sweeps across all possible values from negative infinity to positive infinity. The function f is the joint probability density function, representing the thickness of probability. The dx terms represent infinitesimally small steps along each variable's axis. When we multiply the density by these tiny steps and integrate, we calculate the total volume under the probability surface. This total volume must equal 1, ensuring absolute certainty. Now that we have our normalization formula, let us apply it to a continuous example. Suppose we have two continuous random variables, x and y. They are defined in a region where both x and y go from 0 to 1. Their joint probability density function is given by the formula c times x times y, where c is an unknown constant number. Our goal is to find the exact value of c that makes this a valid joint PDF. To do this, we set up a double integral of our joint PDF over the given region and set it equal to 1. The inner integral is with respect to x and the outer integral is with respect to y. Continuing with our double integral, we can make the calculation easier by pulling the constant c and the variable y outside the inner integral, because the inner integral only cares about the variable x. This is a standard technique in multivariable calculus. We isolate the x part and integrate it first. The integral of x is x squared divided by 2. We then evaluate this from the lower limit of 0 to the upper limit of 1. Substituting these limits, 1 squared over 2 is 1/2 and 0 squared over 2 is 0. Subtracting the lower limit from the upper limit gives us exactly 1/2. This completes our inner integral. With the inner integral solved, we move to the outer integral. We simplify the expression by pulling the constant 1/2 out to the front. The problem has now been reduced from a two-dimensional volume problem to a simple one-dimensional area problem. We proceed to integrate the variable y. Just like before, the integral of y is y squared divided by 2. We evaluate this from 0 to 1. Substituting the limits for y gives us another factor of 1/2. We multiply this new 1/2 by the c over 2 that was already outside the brackets. The calculus portion of our problem is now completely finished. Bringing it all together, we multiply the fractions to find that c divided by 4 must equal 1. This is a simple algebraic equation. To isolate c, we multiply both sides by 4, which tells us that the constant c must be exactly 4. Therefore, our valid joint probability density function is f of x comma y equals 4 times x times y. If c were any other number, the total volume would not be 1 and the function would be physically impossible as a probability distribution. We have successfully normalized the continuous joint distribution. Having seen how joint distributions work, let us introduce a new concept: marginal distributions. Sometimes we have a joint distribution for multiple variables, like height and weight, but we only care about one of them, such as height. To find this, we calculate the marginal distribution, which gives us the probability of one variable while completely ignoring the others. We achieve this by mathematically removing the unwanted variables from the picture. If the variables are discrete, we sum over all possible values of the unwanted variable. If they are continuous, we integrate over all possible values of the unwanted variable. It simplifies a complex joint system into a single focused perspective. Let us look at the mathematical formula for a continuous marginal distribution. To find the marginal probability density function for just the variable x, we take the joint density function of x and y and we integrate it with respect to y. In this equation, f subscript x of x represents the marginal density we want to find. By integrating with respect to y from -infinity to +infinity, we are essentially squashing or collapsing the y dimension completely out of the picture. What remains is a new function that only depends on x, telling us the probability density of x regardless of what y happens to be. To truly understand what this formula is doing, let us look at a visual representation. Here you see a three-dimensional surface representing the joint probability of two variables happening together. Imagine shining a bright light from one side along the y-axis and looking at the shadow it casts on the back wall along the x-axis. That two-dimensional shadow is the marginal distribution. It shows the behavior of the variable x when the variable y is completely flattened out and ignored. The volume of the 3D shape has been squashed into the area of the 2D shadow, perfectly illustrating the math we just discussed. Before we move on, let us see this marginalization process with a concrete, discrete example. Suppose we have two random variables, x and y, which can each be 0 or 1. We are given 4 joint probabilities for all possible combinations. Before finding any marginal probability, we must first check the normalization rule. We add up the chances of every single possible scenario: 0.4 plus 0.2 plus 0.1 plus 0.3. The sum is exactly 1.0. This confirms that our joint PMF is perfectly valid, capturing 100% of the certainty. Now we are ready to find the marginal probability. Continuing with our valid distribution, we want to find the marginal probability that x equals 0. To do this, we must sum the joint probabilities for all cases where x is 0, completely ignoring what y is. We calculate this by adding the probability of x being 0 and y being 0 to the probability of x being 0 and y being 1. We substitute our known values: 0.4 plus 0.2. The final result is 0.6. This means that if we completely ignore the variable y, there is a 60% chance that the variable x will be 0. We have successfully isolated one variable from the larger group. Now that we have mastered the math, let us discuss why joint probability mass and density are absolutely critical in the real world. The truth is, variables rarely exist in isolation. In weather forecasting, temperature, humidity, and wind speed all interact with each other to create storm systems. In finance, the risks of different investments are deeply tied together. If one major stock crashes, another might crash too. By using joint probability density functions, analysts can accurately model these complex relationships and protect against massive losses. Without these tools, we would be forced to treat every variable as completely independent, which would lead to disastrously wrong predictions in almost every scientific and engineering field. We have covered a lot of ground today, so let us review the key takeaways. First, probability mass and density functions describe exactly how our total certainty is spread across multiple interacting variables. Second, remember the distinction. Discrete variables use a probability mass function, where probabilities are added, while continuous variables use a probability density function, where probabilities are integrated. Third, in both cases, the grand total must always normalize to exactly 1, ensuring a valid reality. Finally, marginal distributions allow us to isolate a single variable by mathematically squashing out the others. You now have a solid foundation in multivariate probability.